Welcome everyone to LiveQL Episode 1. Today we have Nico Weissman, Senior Director of Security Research at GitHub, in conversation with Aditya Sharad, Engineering Manager for CodeQL Core Technology. Take it away, gentlemen.
Thank you, AJ. I'm excited to be here today. How are you doing, Aditya?
Hi, Nico. I'm excited to be here as well. I think this will be great.
All right. So this is going to be the first of hopefully multiple LiveQL Twitch streams. I don't know how you call it, shows, if you want to. And the idea will be to sort of look at vulnerability classes and just learn about the vulnerability class itself, and then look at QL and how we can resolve some of those bad classes and build those patterns with CodeQL.
Great. And for those of you joining, by way of introduction, we work at GitHub and with GitHub Security Lab. I am an engineering manager that works on the CodeQL core technology. And if you want to find out more about what that is, what CodeQL is, how you can use it to find vulnerabilities, check out the GitHub Security Lab website or the link codeql.com to just get you started while we talk about it.
Sounds good. And on my side, I'm Nico Weissman. I'm the head of the GitHub Security Lab, mainly focused on security research. And again, if you want to learn some of the work we're doing, go to the exact same website, securitylab.github.com. All right, let's start with our first edition, which is going to be around a very old vulnerability class, but rather new, or still alive, I would guess. So we're going to work around string copying. And I know some people will be face palming right now because string copy is as old as string copy vulnerabilities are old as, pretty much security itself. I was trying to track down vulnerabilities around string copy, and it's really hard to track down the first one. I do remember that one of the first papers about Stack Overflow, and this is not specifically to string copy, but a lot of Stack Overflows were very tied into the string copy function. One of the first papers around Stack Overflow exploitation was the well-known Smashing the Stack for Fun and Profit. And that was in 1996. So pretty old. And I'm sure they were older stuff. I think Match also wrote a paper about Stack Overflows at some point. I think it's even early that Mashing the Stack from LF1. Anyways. For those who are new, we're going to talk a little bit what the bugs are, and then we're going to look at one specific bug class related with string manipulation. It is not the one that you probably are thinking about, which is the most common one. All right, so we're going to do that interacting. This is not encrypted at all, so send your questions as we go. We'd love to learn what you think about. If you're not clear enough, if you let us know, and we will be more than happy to stop and try to address some of those questions. So let me start by sharing my screen, and this is going to be a virtual machine which is running and Ubuntu. We are not going to work a lot around exploitation, at least for this edition. We want to concentrate on vulnerability classes more than anything else. So let me start with string copy. And to do that, let's write a very basic C program that sort of has this vulnerability. Hopefully my C is good enough. I haven't done a lot of C in a while.
And, so you're not supposed to write stuff on the fly and live, right?
I was about to say that. So please be very merciful of us, because we are going to be doing that a lot during this stream and in the future. So please, I'm going to make a lot of mistakes. So please, have some patience. So we're going to do just head start. And then I promise you, we're not going to be about like the normal string copy overflow, but just to sort of like get us into content, we're going to do like a very basic string copy, right? So what we're going to have is we're going to have 3 buffers. I'm going to call it buffer 1, 20, buffer 2, 20, and then a third buffer 20. And to be honest, like instead of like doing 20, let's do max size, as people actually do on code. Using, okay, here we go. All right, so what we're gonna do is we're gonna overflow the buffer 2, which is in the middle between like 1 and 3, and see how that goes. Just to make some, add some content, buffer 1, I'm gonna fill it with characters array. Actually, max size. All right, here we go. And the same is gonna happen. I know I forgot. The same is gonna happen with the buffer 3. And the one we are going to overflow, pretty simple, is going to be buffer 2. For those who don't remember how or never dealt with C in the past, the way string copy works is copy a string up to the null termination byte from destination to source. So in this case, buffer 2 is going to be the destination, and the source is going to be the first argument of this program. I'm not used to using Ubuntu on these machines, so I'm gonna have some problems with my shortcuts. All right. So we have our exercise here. All right. And need to include string, but I think it's still compile. So now I'm going to run the software, and theoretically it should crash. And let's do 30 bytes. Here we go. Before we do that, as a way to show the content, what we're going to do is we're going to print the content of buffer 1 and buffer 2. So buffer 1 is going to be, and Bram is going to get excited soon. Buffer 1.
I think it's pretty interesting just to see how you set up something so that you can look at what's happening in memory and then look at the results in a very simple way.
Yeah. Yeah, instead of like debugging, again, this is going to keep happening. Instead of like going and debugging with GDB and all of that and wasting that time, what we're going to do is like basically creating 2 strings around the buffer we want to overflow. And then when we overflow, we're going to see that A and B are getting overflowed by our string. And this is, again, pretty simple. We're going to use C, just, and I didn't recompile it. All right. A and B. What's going on? Did I make it 0x20? No, that's 20.
There we go. Mm-hmm. Okay, so just I'm going to talk through my understanding of this because this is very different from the kind of process that I normally follow. So you copied strings from the input into buffer 2, but because buffer 2 is sitting in contiguous memory between buffer 1 and buffer 3, what you've written into buffer 2 has now overflowed out into buffer 3.
Correct. So what we're going to see here is that if you're looking at the stack, we have theoretically buffer 1 here, buffer 2, and then buffer 3. This is indeed full of A's. This is full of B's. And then when we perform the string copy, what happened is like it goes all the way with the C's up to overriding some of the C's over here in buffer 3.
So why does it let you do that? Like, it feels like if you've said that thing is of size 20, then it should be able to, the copying function should be able to stop, at the time.
It should, probably in high-level languages, but C string copy is very, very straightforward. It will copy without looking at the size of any of both the destination or the source.
Okay.
So the first thing that people thought to sort of like fix that was to use string and copy, which does exactly the same thing. It copy, but it uses size boundary,
okay.
right? So destination, source, and the size you want to overflow, the size of the destination. And this is an important fact because like, if you look at some of the code and you will be surprised like how many of those happen in the wild, like people sometimes put like size of source.
Right. So if your source is much bigger than your destination, then this will very obediently take the size that you give it, and it will write beyond what the destination might be able to fit. Exactly.
I'm pretty sure, maybe not with string copy, maybe you have seen that with mem copy, which is similar, but for like every memory. We have seen, I'm sure like there's been a lot of bugs like that in 2020. So this is not something from the past, definitely things that happen. Now, you might see it on string copy, probably not anymore. So what the problem with string copy is the following one, which is what we're going to do here is we're going to make that mistake. I'm going to make string copy, and we're going to do the size of destination. So let's do that. So the size of source. So in here, what you should do actually is put the size of the destination, not the source. Mm-hmm. So we're going to do that. And the problem with string copy is that it doesn't, if the size you're trying to write is exactly the size of destination, then it will not copy the null terminate byte.
Okay.
So that means that if you print that string or do any other operation around string copy, it might or might not found a null at the end of that string. And it could lead to many problems in the future of that string. So for example, if you do a string length,
like going through the history of like string copying functions, I guess, right? So we started with string copy, which did not let us specify the size, and string copy is a little bit better because you can say what the size is, but it doesn't quite do what you expect because it doesn't have the null terminate. Okay.
Exactly. So the answer to all of that was to use string copy, which I think it came out from the BSD team. And what string copy does is exactly the same thing as string and copy, but instead of using the full size, it does a full size -1 and adds as a null byte at the end of the buffer. So it makes sure that whatever you're copying is going to have a null byte at the end. Of course, if the size is bigger than the destination, then you're gonna have an overflow. Oh, that's like if you're not implementing it the right way, you're gonna have an overflow. But at least you can control.
But if you give it the right size, then it's going to do something sensible with the right size.
Exactly, and we can try to do that. Let's see. I did it again. This is gonna happen all the time. I'm sorry about that.
Oh, I think that needs to be argv.
Yep. And what we're going to do here is we're also going to print a buffer too. So one of the things that I forgot is to make an include because it's not on the regular library, and include is bd/string.h. And the way we have to compile it is we have to add a little -lbsd. Here we go. Simple. Now we do the overflow. As you can see, it was limited. And you can see here an interesting fact. Like for buffer one, we actually wrote exactly 20 bytes. There's actually no null byte at the end. However, when you declare a stack variable, there is padding around that. And that's why we're not seeing that like a lot of like trashing here. We do see like a weird character here, which should not be there. But that's like reminiscence of the stack. Because with the memset, we didn't actually set a null byte string at the end of those buffers. But what's important here is buffer 2. So in buffer 2, we wrote exactly max size. So in reality, if we have done it with string and copy, and we can do that, let's do it with string and copy and see what it looks like.
Did we write max size -1 because there's a null byte at the end? It looks a little bit shorter in the output.
Exactly. So as you can see, like with string and copy, it actually wrote 20 bytes. Right. And then we see this weird character, which is like the buffer size +1. And then there's a null byte after that. So with string and copy, we don't have this problem. And as you can see, compile it again. As you can see, it's been printed well. There's no like weird character at the end of this buffer. All right.
Okay.
I mean, that's like 15 years ago or so, like vulnerability class in terms of vulnerability classes. Now, let me show you the actual vulnerability class that we want to discuss in this session. So one of the interesting things, if you look at the string copy, and hopefully I have the min files. Oh, I did it again. Oh no. All right, so if you go man string copy, hopefully I have the mans here, is that very basic. What it says is like, it's a function that copy and concatenate strings respectively, safe and error prone, and warranty that the result string is null terminated. That's perfect. Now, if we look at the return value, and you will see something very interesting in this specific line. It says the string L copy and string L cat functions return the total length of the string they try to create. And I think what's key here, yep. The key thing here is this try to create. So what exactly try to create means in this context, right? So let's try to figure out what it means, right? So what we're gonna do is I'm gonna create a variable size t length, and then I'm gonna put it here. I'm going to print it afterwards. So length. There we go. So let's see how that goes. What did I do? LD. I'm still going to print.
So that's kind of
very
confusing,
interesting, right? It is confusing.
We asked it to print. Okay, yeah, maybe you should.
Before we go into that, let me do the following. Let's do that. Like, I'm gonna ask, what is the size of buffer 2? All right. So we have the size returned by the string copy and the size returned the actual. The actual string length of buffer 2. All right, we're gonna see it in a little bit. So, yeah, now we're getting into a good place.
What?
So we have buffer 2. Go ahead.
Yeah, maybe I'm just gonna try and talk myself through this because we asked it to write 40 characters. Yeah. Of course, it realized that it did not have room to write 40 characters, and it only wrote 19, and then it left one space for a null terminator. So this means that if we ask for the length of what went into the buffer as a string, we get 19. But if you ask for the kind of value reported back by the copying function, it's 40. It's the thing that you asked it to write and not how much it actually wrote.
Exactly.
And yeah, so if you're expecting one to be the other, you're probably going to have a bad time.
Correct. And
now,
that
is that a thing that you might do? Like, would you expect that? Would you use the return value?
That's a very good question. And the answer to that, it depends on the developer. And this is one of the interesting things about like auditing C code is that, and especially me, that I have like a very short memory, as like people from my team might have experience, is that sometimes when I'm auditing, I'm like asking myself, like, what exactly will this return? And I keep doing that question for like a lot of different functions. And that's part of like my lack of memory, but at the same time, it goes as an advantage because sometimes like you really forget like what's supposed to be returning certain functions or like what is supposed to this argument be doing and all of that. So there is a whole experience around like auditing by using man files. So like actually looking at the implementation of certain code. And the interesting thing is also like sometimes people tend to create wraps around functions. Like for example, you will see that string copy, since you realize that to compile it, we need the LBSD library and things like that. What some projects do around that and other libraries is like they write their own wrappers. What they say is like, if string copy is already implemented, let's use string copy. Otherwise, use my own implementation of string copy.
Right.
And with this, string copy is example of that, but you will see that a lot in some other functions. The interesting thing about that is like sometimes you have to look at that implementation because it might be different from like the actual string copy implementation. It might work exactly the same, but the return value might be different. And then it might expect different things from like a normal string copy. And by that differentiation, you might find like vulnerabilities through that way. In this case,
interesting that like even if you being experienced at auditing this kind of code and looking through these, if this doesn't stick in your memory, it's pretty reasonable to expect that for someone else maybe coming into a new code base or who's developing something and has jumped around between what they're working on, might also not remember the subtleties of what this is returning and what that intended meaning is. So these are really non-intuitive in that it's not immediately obvious to you what you're going to get back out, and whether it's the number or half the number or the number -1 that you expect.
Exactly. So let's make an example of that and how these can potentially be exploited. So the way we have seen it in a lot of different code bases is the following. So what we see is like this one string copy, because like when you see that like someone is using the return value of the string copy, that means that they're going to use the return value, right? Like nobody like just get that. There is some exceptions around that because like sometimes they want to check if we are copying more than the actual max size. So there's some reminder left. But in general, when you see someone using the return value from string copy, that means that they're going to use it for something. So a good example of that is like another string copy to write some other string into the same buffer. So generally what they do is like they copy the same buffer too, and they use the return value as an offset.
Okay, so you're kind of copying things in a sequence into the same buffer. So you're doing string concatenation, I guess. You're building up a long string which has a bunch of segments that you've placed in.
Exactly. So we have, in this case, we are using the first argument and the second argument of the function to copy it all into buffer2. And this is valid. Like for example, if buffer2 is enough and we're not, overflowing on more than we're supposed to, then we will be copying like these two buffers in the same function, and that will work pretty well. So what they do is like they use the length that we see in here as an offset to where to start copying the second buffer, the R2. And then in terms of the size, since they don't want to overflow, what they do is they use max size minus that length.
Okay, so after the first time, I hope that I've copied length, something into the buffer, and then I start at the end of that string that I copied, and then the amount that I copy the second time is the space that I think is left.
Exactly.
Okay, so that would make sense if the length were really the length.
Correct.
That I actually copied, I guess.
So let's start with that and use it in a valid way, right? So we're gonna compile that. And then what we're gonna do is gonna run the exercise with a X and a set. And what we're seeing is exactly that, right? Like first argument, and then the second argument is being copied into buffer2. Everything looks fine. The length is 5 bytes because the length, remember, is the return value of the first string copy, which is like those 5x. And then the final string length is actually the string length of buffer2 after we did the 2 string copy. So that's 10 bytes. Sounds
Okay.
good. Now let's start like making some fun. So we start adding more X here. And what's gonna happen is that, so far so good. We're gonna add the, what happened here is that we buffer, the first argument is like 19 bytes. These X are actually, let me do it with Python so it's much clearer. So we're gonna actually copy 19 bytes, and then we're gonna add some sets at the end, right? So that's perfect, it works well. Why it worked well? Because it went here, and the return value was 19 bytes. So it actually did max size minus 19, and that's gonna be 1. And that's okay, and we try to copy 1, but since string copy does size -1, it's actually end up copying nothing at all. And as we can see here in the result, we got a normal buffer2 without the set included. We have gone 1 byte less, 18. Then we see the 1 set at the end. Right? What happened if we go 1 byte more? So far, so good. But if you do 30, then something weird happened.
So we started writing in the wrong place because we wanted the Z's, Z's to go into buffer2, but we ran out of room in buffer2. And I guess the offset where we started writing was outside of buffer2.
And let me do the following. Let me just, so we can look at as how the stack will look like, I'm gonna order it this way.
That makes sense. Let's do that.
So as you can see here, what happened is that buffer2 actually copy all the C's and then copy the sets after that. And then the set end up being overflowing buffer3. And let's use one, and you can see like the length of the whole thing when we did the first string copy was 30 bytes.
But it didn't actually copy 30. We asked it to copy 30 and it copied 19.
It's getting interesting, right?
Okay, so this is quite subtle.
Yeah, it's quite subtle. So let's understand what's going on here. And to do that, we're going to basically replicate what arguments are actually passing through string copy. So we're going to put like, this is going to string copy of buffer plus 2 plus length. And then it's going to be arg2. And then what we're going to do is exactly subtract max size minus length, right?
Mm-hmm.
And so in here, what we're going to do is this is going to be length, and then the argument is going to be max size minus length. So basically here we are like showing out what's going to happen with the second string copy. So as we can, oh, I forgot to do a line break. Here we go. All right. So now we're game. So what's happening is the following. It's starting to copy, first of all, that's ability right there. Like no matter what the side thing is going to happen, is that we are starting to copy at buffer2 plus 30. And remember that the size of buffer2 is 20. So we already, like whatever we are writing here is going to overflow. Like it's passing the boundaries of buffer2.
Mm-hmm.
And then of course we're copying the content of argument 2. And then what is the size we're copying? Minus 10.
That seems bad.
That is definitely bad. So of course, like if you can see is the way stringal copy works, is the third argument is a size t, and that means it's an unsigned integer. So
if you give it something negative, it's going to underflow into something really, really large.
yes,
Okay.
yes, and unsigned. So that's where the magic happened. Of course, in this case, since it's stringal copy, it's not going to like overflow all the way. Like if it was mem copy, what happened with mem copy is that it's actually going to take that size and going to overflow whatever is on that size. So if it does say minus 10, which is going to be a large number on as an unsigned, it's going to try to copy that amount of unsigned byte. But since stringal copy always stop when see a null byte, then it's only going to copy as much as RB2.
Okay.
So that's what's happening. Like we end up overflowing buffer 3. And that's the bug. And we can see multiple different bugs around that. Like it could be with the second function can be a stringal copy. It can be as an printf. It can be a mem copy. It can be any function that copy memories to one. It could be a stringal cat too. It's weird
something
that
we're expecting like a size argument, right? And then if we're using that size argument that's derived from this calculation that stringal copy gave us, it's not going to be necessarily at the position that we expected.
Exactly.
Okay.
Exactly. So now that we identified the vulnerability class, and of course, like the way you will exploit that in all computers, and I'm going to go about like bypassing all the different security implementations nowadays, but the way you will do it long time ago is that you just overflow the return address and then you get control of EIP. Now, the interesting thing about this specific vulnerability is that it's not just a stack overflows. If you can control length, then you can like modify the offset to move it around and potentially, bypass any like canary token restriction or things like that with that offset. So there are like many ways you can potentially exploit that in modern operating systems. But
I won't even notice that you've like smashed the stack canary or done other things like that. You can bypass that because you control exactly where you're writing.
Exactly. Okay. So taking that aside, let's start to look at QL.
Okay.
Let me stop sharing and let's see how someone will auditing this work. How someone like start modeling that vulnerability class.
Great. So what we kind of talked through here, and there have been some very interesting comments on the chat about, the value of talking about both the vulnerability side of it, and then, can we get to the QL? So I think this is very interesting in that I want to know very clearly what the problem is when I start to write a query, or at least have some idea of what the pattern is that I'm looking for. And I think what you've shown me here gives me a good idea of that, right? I'm looking for these particular functions, these particular string copying functions, and I know what their arguments mean now. And I also know that the return value is interesting and the size arguments are interesting. So with that knowledge, let's write some CodeQL. And what have I got here? I've got a CodeQL extension for Visual Studio Code. If you've been following along with GitHub Security Lab and associated technology, this should be familiar. I've got a database of some open source code. This is Apache Guacamole. I've taken this from a historical point in time, so it's a fairly old database, but it's got some interesting patterns in it. And I've got a starter workspace, which has the CodeQL standard queries and libraries and the ability for me to write my own. So let's write a new query for ourselves. In order to start doing anything interesting, I need the standard libraries for CodeQL for C and C++. And what do I want to look for first is, I guess to start with, I want to see whether this API you described is being used, right? Do we use these string copying functions? Are they in the code base at all? And maybe I can describe them in a nice way. We know them by name. We know there's a particular kind of function call. So let's say something like string copying call. And what kind of thing might this be? It's probably a function call. I'm just going to make my editor a bit bigger. So I'm using the function call from the standard library. Now that I've defined my own class, this will describe a set of values. I need to say what it means to be a member of this set of values. Well, I can get the name of this, well, I should get the target of the function call because it's a call. The target will tell me the function that I care about. And now I can get its name. And you mentioned a couple. You mentioned, string L copy, string L cat. Maybe let's just use those. String L copy. There's no O.
There we go.
And string L cat. Let's start with those for now.
Mm-hmm.
And well, I know some other information about these. I can get the return value because that's at the point that I call. But maybe I also want the size argument. So let's write a member predicate on this class, which returns an expression. That's the argument of that particular call. Say it gets the size argument because that's what it does. And what do I want to say? This dot get argument. Now string L copy and string L cat have the third argument as the size, if I remember your example correctly, because we are
Correct.
We are programmers and we use zero indexing. This is 2. And I equate this to the result variable. So it says this returns the second argument, or the argument at position 2 of this call. All right, so let's look for these from such as call. And let's run this query. And I got nothing.
Nothing. Have you tested this query before?
So I guess you mentioned that people write wrappers around these functions, right?
I do.
And so maybe like names are a very strict thing to match on. Maybe they've got their own version of it, something like that. What we can do is try to match this a little bit more generally. So let's say something like, I know, matches. Let's do a regex match. And then I can have anything at the beginning, and then I have string copy or string count. Let's see if this does any better. I can account for the fact that they might have written some naming prefix at the beginning. That is a little bit better. Okay, because this is guacamole, they have guacamole naming, so everything is guac. Great. Now, what do these look like?
Now, not for this session, but I will definitely look at guac straight like copy and make sure that that the return value is doing exactly what we're expecting to do. But it is, right, because we already check it out.
We had a look at it. Okay, so I see a bunch of these calls. There's a whole bunch of them. I mean, but there's maybe some, and there's some that are guac strill cat. There's some that are guac strill copy. It's good. I can handle both of those patterns reasonably well. This one doesn't use the return value, so maybe that's not very interesting. Here we have the length. We use the length, but then we check it and we do some kind of bounds checking. So maybe that one is okay. This one kind of looks like the pattern that you described, right? We do this string copy. We get the length out. If it's beyond a certain size, we bail. But then we use it again we do exactly the pattern that you described, right? You subtract from the length, and then you do another copy, and you keep doing this a few times.
And that's exactly what you will end up seeing on functions that implement that in the correct way. That as soon as they get the length, they will check it against the third argument of string L copy.
Right. Which is what we had in the size over here. This one doesn't seem to check it against the length. It checks it against 0, but it doesn't look like it checks it against the the bounds that you might expect it to be limited within.
Mm-hmm.
So that one looks a little bit more concerning. Right now, of course, this query is not super interesting. I've just looked for all the calls. You can do this with grep, but we can, knowing that there is some interesting examples in these results, maybe we can improve our query to actually look for the pattern that we care about, right? And so what is interesting here in this problem that you described is we want to see the return value of this, and we want to see whether it ends up in the length parameter of another of these calls. Sorry, the size parameter of another of these calls. So to do that, we talk about something much more complex in CodeQL, the flow of data through the program. I want to see that the value in the first place flowed into the value in the expression in the second place. How do we do that? Well, we import the libraries that allow us to reason about data flow.
Which describe a lot of vulnerabilities, right? Like there's a lot of vulnerabilities are around like data flow. Like there's a source that ends up in a dangerous sink, a source of certain kind on a sink of certain kind.
Yeah, it's a nice pattern. When we write it, it's a little bit of boilerplate, and the audience will see this in a moment when I write the query. But it's a very powerful paradigm where you can describe this kind of common situation of here are sources, here are sinks, here is the flow of information between them. And a surprising number of queries, as you said, just fall out of this pattern. They all kind of look the same.
Like even if you talk about like web, right? Like an SQL injection is like, there's a source of like something that you control, and then there's a sink of like this source you control ending into a method that query a database.
Right. And I guess cross-site scripting is if your sink is you're writing it on the page, and then you've got kind of the same vulnerability. Okay. So given that all these queries, all these problems have the same form, we describe them in a similar way. We write these configurations, which are really just boilerplate to describe the sources and the sinks. So in this case, I'm writing my own configuration class, which extends taint tracking configuration. That does most of the work. I need to give my configuration a name. Doesn't matter what this is. My configuration needs to have a couple of predicates in it. It needs to have an isSource and isSync predicate, both of which describe the endpoints of this problem. So let me write isSource first. My source is a data flow node. This refers to a point of the program that might have a value. What did I say the sources were? I said it was just the return value of such a call, right? If I get the length out, it might be surprising.
Because all start when like someone returns something out of like string copy or string cat, right?
Right. And so that's not what I wanted. Such a return value is an expression. And in particular, it is one of these calls. So I say that the source is an expression, and it belongs to the set of interesting string copying calls that I described previously. I need to do something similar for sinks. We'll call it sync so I don't confuse myself. And now my sync is not the call itself. My sync is the size argument of such a call. And so I can do something like equals take any string copying call, C, and get its size argument.
So let me understand what you just done. So we have, as again, we are defining a taint tracking configuration to make the data flow that you were mentioning. And then we are overriding two different predicates. One is the isSource, which describes the source of the data flow. And in this case, what we're looking for is the return value out of the function that calls string.copy or string.cat. And that data flow has to flow all the way to the same function or like a different functions that string.copy or string.cat. But instead of looking at the return value as we did on the source, now we are looking at the get size argument that, as we defined, was the third argument of those functions that we mentioned.
Exactly.
So we're going from a string copy to a string copy, basically.
Yeah, and they might be the same, they might be different. You know, it's possible for it to satisfy this condition in both cases, but we're not insisting that they are exactly the same because that would be very narrow. So I've described this configuration, and you have described this configuration. Now I need to use it in a query. Let's add ourselves. We can use these path nodes so that we can have the editor display a nice path that shows us how information gets from one to the other. Use my configuration because that describes the problem. And what do I know about this? I want to say that the config has flow between the source and the sink. And I will select them in a particular order that is only interesting because we want to format the results in a nice way. So I can say here is that, that's it, return value.
Before we actually run it, can you walk me through any? Because I can see that why you're not using any on the source, for example, and you are doing it.
That's a good question.
Target.
Any is kind of cool. We could use any in the source. We could do something like this. This is perfectly valid. And it's exactly the same as what I wrote before. So I guess you have a choice between, you have a value that we've described. The value is source as expression. And we want to say that it belongs to a particular class. So you can do this in one of two ways. Either you can equate it to something that belongs to the class, which is what this equals, and then any value does. Or you can just say directly, it belongs to the class. And so belongs to is instance of. And so instead of an equality, we're saying it belongs to this class or this set. In the second case, we don't really have a class for the size arguments. We could maybe write one, but we haven't. Instead, we can get them as values. We can get them as the return expression, the return value from this predicate. And so I'm going to equate these, but I can only call get size argument if I have one of these string copy calls floating around. And so I can use any to find such a value. For any who have seen exists in any of the CodeQL tutorials or other queries, these are quite similar. You could equally well write this as the same.
We have that question on Twitch right now. Like, what's the difference between like exist and any?
The audience is ahead of me. These are syntactically equivalent. I could say there exists a string copy call, and call it C, such that the sink as an expression is C's size argument. So these are the same. These are just equivalent ways of writing the same query. This is kind of the nice thing about CodeQL. There are many ways to write the same thing. The difference does not matter as long as it is clear to you as the writer and ideally to your readers.
There's no optimization by using any rather than exist or anything among those lines that we should.
Yeah, in this case, the engine, the optimizer will compile them down to effectively the same thing. And so there's no performance gain doing this. My intuition for deciding how to write something in terms of style is this is kind of a one-time use variable, right? If I were saying more things about C, then I would probably use an exists because it's quite useful then to declare it as a local variable and then say some stuff about it. In this case, I only want C so that I can get its size argument. So it feels like a natural place where you can use any. But like I said, it's not meaningful in terms of the behavior of the query. So pick whichever one you find is most intuitive for you. Now I've written this query with this particular structure. I will also import a little extra library that allows me to visualize the graphs in the editor. And I will add some metadata. Again, this is not super interesting from the point of view of you as a researcher, but just to make the tooling work, we say that this query is formatted in such a way that it will produce graph results or path results. And now I will run the query. Of course, this will take a little bit longer because we have started to use a much more sophisticated library, which needs to be compiled and then evaluated in order to understand the flow of data through the program.
And let's talk a little bit about the flow of data. Is this happening inside a function? Is happening between like interfunctions? How that works?
Good question. So there are different levels of the data flow and taint tracking libraries. There is a local variation, which is you can do taint tracking local taint, and this will track the flow of information within a single function. This is quite feasible to compute, so we can actually compute it for every single function in the program. However, this is pretty limited. In our example, if you had done this string lcopy call in some other function, and then you return the value back out, and then you ended up in some other function, local taint would just completely fail to catch that. So it's a good place to start in terms of writing your query, but it's limited. So, maybe you can do, if you're writing a query, if you're listening in, you might want to start with something local, and then you can gradually build your way up to using this configuration. And the difference in using this configuration, and this has flow path situation, is that this is global flow. It is interprocedural. It is capable of reasoning about the flow of information across function boundaries. And we can see, and we can inspect in some of the results whether we actually managed to get any interesting results in this code base that cross function boundaries. Of course, you pay a price for that, so it's slightly more expensive to compute, which is why we have to narrow down our sources and our sinks to something pretty manageable. If these are very huge, then your query is going to take quite a while to compute. So what have we got here? We've got a set of results.
I'm curious.
I can expand these parts. This is always quite fun. This is one of these.
So what we're seeing here is that number one is the source and number two is the destination, right?
Yeah.
Or the sink.
This is, indeed. These are similar. Now remember, we spoke about the kind of bounds checks, but we haven't done anything about them in our query. So this is just from auditing point of view, finding all the calls to string copy whose return value might end up in this length argument. And we notice that it handles this subtraction operation fine. This is because we use taint tracking and not data flow. So we're fine with these minor changes to the value as long as some value is derived from the length, probably with some arithmetic involved, we're still going to catch it.
Perfect.
And this is one of the interesting ones I think that we described, right? There's no bounds check against the length. I won't go through all of them. Oh, this one has some possible paths. There's some variation. There is a conditional, which is guarded by this macro over here. I can jump to the definition and see what it is. So I see that there's this macro that actually does a size check before it attempts the subtraction, and it actually kind of bounds out at 0 if you're doing something invalid. So these are false positives because there is a sensible size check, and we can think about how to tackle that in a few moments. But for now, we are at least convinced that this analysis is perfectly capable of looking through a few layers of interaction and describing to you these multiple possibilities for how you might end up in the size argument of one of these string copy calls. Again, like I said, I won't go through all of them, but it's quite interesting that you're capable of doing that.
Let's look at some of the ones where it says fs.c.
Let's look at fs.c. What does this do? Well, there's no checks at all. No, not even an attempt at a check.
Pretty straightforward.
What's this doing? It is doing some kind of path computation, right?
Mm-hmm.
Yeah.
Now, of course, to actually being able to exploit that, you need to be able to send a source that is bigger than the destination, like this.
Right. So you need your parent, whatever that is, to be bigger than max path.
Right.
I guess
Sometimes
that means
possible,
that
sometimes not.
in this application, you need like a file system path that is longer than the whatever they're setting for max path is. Maybe that's possible. I don't know.
Mm-hmm. And this is actually the function that we report to Guacamole when we audit this functionality. It was not a bug itself because we couldn't find a place where the parent was like bigger enough than Guac RDP FS max path. However, like we let them know that the pattern there could be potentially dangerous in the future, so they should look at it.
Yeah, and sometimes when you're doing this kind of, even when you're looking at the results of these queries, what we've written here, I think, is an exploratory query. It's a great starting point. Frankly, it doesn't give you that many results, so it's quite manageable. But it's a good starting point to say, like, what am I looking at in this code that is probably buggy? And then you can use your expert knowledge in terms of like whether this is exploitable, what to do with it, that kind of thing.
We have a question from the audience, and is what is the difference between a top-level expression and, say, a call? In the U-Boot channel, U-Boot challenge, there were steps where we had to find top-level expression of calls.
Good question. So the U-Boot challenge, again, for those not familiar, this is one of the tutorials on the GitHub websites that involves, and on GitHub Learning Lab, that involves analyzing the source code of U-Boot and finding particular calls. Those were macros, if I remember correctly. So there's a distinction here in our libraries and how we model C and C++ code between functions and macros, function calls, and macro invocations. Macros are, in my personal opinion, quite annoying to model and to reason about when you're writing a query, because they can expand to almost anything. They can have any syntactic element. It doesn't have to be complete syntax. It doesn't have to be fully valid syntax. It is just some fragment of code. However, we can provide you the invocations of these macros, and then you can look at the values that come out of them. So in those cases, the U-Boot tutorial asks you to find the macro invocations and the corresponding expression. So the kind of the main call that comes out of this, because those macros really just wrap function calls most of the time. Here we are in a nicer world. We are dealing with function calls. These are not macros, although we could maybe change the query to handle that case. And so the function call is already an expression. If we follow up the inheritance hierarchy using jump to definition in the editor, we see that it is a particular type of expression. So here we don't need to do this top level expression business because we're already at the top level expression. Yeah, if you're reasoning about macros, work with care. You will then need to probably find the corresponding expression for the macro invocation.
All right, so what happens if we want to add smprintf to this data flow? Because that smprintf is similar to what we have seen here, but the argument for the size constraint is on the second argument, not on the third. So that is going to change the way we are looking at this, right?
All right, so we have, I guess, these, let me just write down the patterns in a boring fashion. So I have string L copy is des, source, and size. I have string L cat is pretty much the same. And then I have snprintf, which is, I forget the first one. It's something like, and then format string.
Format and then, yeah, values.
And then values. Okay, so I've got to handle these separately. And that also affects my get size argument predicate, right? Because I want this index to be based on what I find there. So there are some options for doing this. Because we've written a class, to me, the most natural way is to say that this is a value that is associated with the class. We allow you to declare fields. This is a little bit like a field might be in Java or some other, or C++ or some other language like that. So we can say size argument index.
Kag has a question. How can CodeQL know what c.size argument is on any function? And this is exactly what Aditya is about to explain.
Okay. Yeah, I think some folks have also asked this a little bit earlier where they were trying to make this more general. So you can do this with a lot of exists written within your characteristic predicate. That's this predicate here that defines the body of the function, of the class. But then you have this problem of how do I work out what that value is here in this other predicate? So we're going to declare it as a field. Just remember that everything in CodeQL can have multiple values. It doesn't have to be just one. So you have to handle these with a bit of care. Now this is not bound to a value. It's complaining at me. So let's bind it. So let's write these different possibilities. One way I could do this is I could write something like I have a name. The name is target.getName. And what else do I know about this? Now I have a bunch of different possibilities. Excuse me. Let's go back here. So my first case is that it's string L copy. So I can say name equals string L copy and size arg index equals 2. Or something similar for string lcat. The size argument is similarly also 2, or the name is and the index is 1. And now I need to close my exists. I will format it just to make sure I can read this reasonable way. So I say that the name is the name of the called function. If it's string lcopy or string lcat, then I get index 2. And of course, I've not bracketed this correctly. So let me make sure I do that. Otherwise, my ands and ors will get mixed up. That's better. So either it's string lcopy or it's string lcat and the index is 2, or it's snprintf and the index is 1. And now I had better use the correct index over here. So this is slightly more general. I lost the handling that I had of like guac string lcopy of these prefixes. So I could do something like this.getTarget.getName matches a wildcard, anything at the start, plus this name. I think this is a reasonably neat way of describing all the patterns that we care about.
So let me see if I understand. So for the first function, we are looking at any function whose target, which is like what we are calling, match string lcopy, string lcat, and sprintf. And for each of those, we are assigning which is the argument index of the size that we're looking for. So for string lcopy, it's number 2, string lcat, number 2, and for printf, number 1.
Yeah, and then we attach that value together with the current value in the class, and we are allowed to access it over here. This example is neat because there's only one possible value for each such name, but you could write many. You could have a 2 or 3, and you could do all sorts of stuff like that.
Are we assigning the value 2 to size our index? Is that how you should think about it?
Probably a better way is to think about it as asserting that 2 things are equal. So you say that these are not assignments, also because you can write them the other way around. This is perfectly legal, and so this trips up a lot of people who are used to assignments. Yeah, I think of it as an assertion of equality. Any variable can have a whole bunch of possible values. They are determined by its type. So in this case, an integer variable must be a 64-bit integer, 32-bit integer. And you then decide what the possible values are narrowed down to. So by writing such an equality assertion, you are asserting that in this situation, the value of this must be 2.
All right.
Someone on the chat mentions it's like a filter that takes the multi-valued result set. That's another helpful way to describe it. So think of these as, it's worth developing your own mental model of like how you want to think about these. I like to say there are sets of possible values or tables of possible values and predicates, and then they are narrowed down through these assertions based on what you write.
I have to make that, when I start with CodeQL, I have to make that mental model of filtering rather than like assigning personally, because I kept thinking the wrong way. And by like starting to think about like filtering instead of like assignment, it like helped me understand better what I'm looking for.
Yeah. And another common one that trips up is just multi-valued. Like if things can have multiple values, it makes sense when you need to reason about things happening many times in your code base, right? There won't be only one of these calls. There could be many, but it takes some time to get used to that.
Now, the way you set up this configuration for the data flow, that means that now the data flow can flow from a string snprintf to snprintf if I want to, or from an snprintf to a string lcopy, or like any of those combinations.
Yeah. Right now, I'm not really insisting that it's the same kind that ends up in each end. I can flow from any one of these into the size argument of any other one of these. Maybe that's okay. I think that seems reasonable, at least for the problem we're describing. We could be fancier and we could add it to the configuration and say, this is a configuration that only applies to this particular kind of string. But it feels like overkill.
So this is sort of remind me of that vulnerability that Kat found some time ago on, I think it was RSys log, if I'm not wrong.
I believe so.
And he was not looking at string copy or string cat, but rather snprintf, right? Like I think the way it works. You might have the database around, or
I do have the database.
okay, here we go.
Conveniently, let's run this query on that database. This was, for the audience, this was the open source project rsyslog, who again, this database is from April 2018, so that was the time at which they fixed it. We're not dropping 0 days here. And they had this interesting vulnerability, the same pattern that we described, but with snprintf, and which one of our colleagues in the security lab found, reported, and they, let's see if I can find the right one. I think it was this one. Yeah.
Let's look at the code.
So you got this same pattern over here where you call, in this case, you call snprintf, I think, in a loop. So we have this
interesting
loop.
Because Dataflow understand the loop and understand that the flow of information will eventually move like on the first call to the second call of the loop, right?
Yeah, it's able to, it's not, and many people ask about this, like, does it get stuck if there's a loop? Does it like, Stack Overflow? And we're like, we're reasoning about what the program does statically. So it will be a recursive calculation to figure out that here is a graph which has a cycle in it, but we're not going to try and unroll all the possible values that the loop might have because we're not running the program, which is kind of nice. But yeah, as you said, it does know that this is a loop. So this statement will be followed in some control flow path by potentially the same statement again. And that means that the return value that got added into all names might end up back in here in this subtraction where we subtract all names. I believe for snprintf, you have to add some other conditions that say like your format string is going to allow you to add something unbounded. So you need something like a %s or something similar in the format string. Otherwise, if you fix it to like an integer with a limited number of places, then you can't get it to overflow, so it's fine.
I mean, eventually you could potentially do it, but you will see more cases around like strings rather than integers or other.
Yeah. And I guess in all cases, you could still have this bugginess of you started in the wrong place. You just wrote it in the wrong part of memory. It might not overflow, but it's not doing what you want it to do.
That's very interesting. So I know it's not the scope of this conversation, but as part of a blue team. So what we have done so far is basically exploratory queries, right? Like we are looking at code, we are understand a specific vulnerability class, and we start like building a class to find different cases. As you can see in Guacamole, we find like 21 different entries that has that specific pattern. But of course, out of the 21 entries, there are a bunch of them that has like guards and all of that. For me, as security researcher, that's good enough. Like 21 results is something that I can, look at it in like 20, 30 minutes top, at least to identify like 2 or 3 functions that I think are good. But as part of like a blue team and, connecting CodeQL into my CI/CD, having, let's say like out of 21, I have 3 good entries, like having like 18 false positive. It might like bring some friction into the.
It's not great if you have that, and I guess you want developers to grow their security knowledge, and you can't have that if they're unhappy with the results that you are giving them. Great. So I think that's a really interesting point you make about kind of what different security teams might need, these different uses. I think in terms of queries, there are really 2 ways of thinking about a query. There are 2 possible queries that you might write. We've done kind of an exploratory query. So this is something that, security lab researchers will use quite a lot. Folks who are contributing to our bounty programs will write often. We're exploring the code base, right? We're auditing it. We're figuring out vulnerable patterns. We're kind of getting more precise as we go. We're building up a query to be more meaningful, like you see me do today. But we accept that as long as the number of results is manageable in some human sense, it's okay if there's a little bit of noise because we know to manually look them out. So then the other kind is really a production query, something that you would run, as you said, in CI. You would run it on, like GitHub code scanning if you had that enabled. Then you want something precise. You want to be able to say with reasonable fidelity, like, this is probably a problem. Let us give you all the information that you can have to fix the problem.
And like everything that happened in production, it's take more time and it has to be like much better quality than what little hack we came out.
And we also try to encourage people to run this kind of analysis at code review time. And if it's coming on your pull requests, you really want them to be sensible results. Otherwise, you're going to be deeply unhappy with whoever is giving you this tooling and analysis. So with that in mind, I think it's useful as query writers to think about exploratory versus production. Often an exploratory query can make its way into production. That is perfectly reasonable. Now to the specifics. How can we do that for this query? Well, the main obstacle here is that we haven't worked out places that might sanitize the length value or bound or restricted, or not, in other words, make it safe. We've only talked about the sources and the sinks, and if you're following along with this terminology, there's this other aspect of what is a sanitizer for this problem. Have I protected it? And with these examples that we saw that we kind of verbally agreed were false positives, the pattern was that there's a check, right? And then in one branch of the check, you don't get the same value, it's just 0. The data flow analysis will take care of that. But in this branch, we know that this is a safe length. It's been checked, it's all right to use. So let's look at the configuration and see what it enables us to do. It has a bunch of predicates defined on it. I'm just going to close these results for now. It has isSource and isSync, which you've seen me use already. It then has isSanitizer. So that's a place where you might have a single node in the data flow graph where you want to stop the flow. This is good if you have something like you're talking about SQL injection, cross-site scripting, and there's maybe a sanitization function that does escaping. And then if an argument goes into that, you're safe. Assuming your sanitizer knows what it's doing. We won't get into that. What we have here is a little bit more involved. It's not so much a single place that gets sanitized as like a condition. And if you're inside that condition, you're safe. And if you're outside that condition, you're sunk. And so there is a hook for that. It's a little bit more involved to explain, but we can use it. These, I think, are called barrier guards or sanitizer guards. So the definition here says it holds if data flow through nodes guarded by guard is prohibited. And if we describe these in our configuration, the analysis will take them into account when it calculates flow. But this means I need to construct something of this barrier guard type, a guard or a condition that validates some expression, and I need to describe what it checks in what branch. So let's start writing one of these. And I'll talk myself through it and convince myself at least that I'm on the right track. First, code snippets are useful. If I do something like if length is less than some bound, then I guess it's safe to use length. And if not, then it's not safe to use length. Simple check for the overflow. There's the dual of this because I don't know which direction my comparison might happen, which looks like this. If it's bounded below, you saw something that checks against 0 but not the upper bound. Well, I'm still unsafe in that case, but it's safe if I'm bounded. Mm-hmm. So I want to handle these cases. Let's give myself a class name. Let's say Comparison Guard, and it will extend data flows barrier guard class. Now, as with all classes, I need a characteristic predicate to say what is in this class. What is the value that happens here? I believe these kind of comparison operations are called relational comparisons. And I will make sure by using the autocomplete because I cannot have all of this in my head at all times. So a relational operation is one of these, greater than, less than, possibly with an equals to. Great. Good enough to start with, but the compiler is still not happy. It says it must implement this method defined on the supertype called checks. Well, let's do that.
I have never used barrier guards, so I'm like really excited about what's happening right now.
They're quite neat. I find them a little bit difficult to write on the fly, so this is a little bit nerve-wracking, but we will see how it goes. And I believe this also accepts a Boolean. It does accept a Boolean, so let's give it a Boolean. Okay. So what is this? What is this saying? This is kind of confusing to read, but checked is the thing that gets checked. I want it to be this length in this example. This is why I wrote the examples, because you can't live without them. So checked is going to be this. Parity is in which of these branches is it safe? So I will say one or two possibilities. Checked equals this, and I'll cast it back to a relational operation. And I can get the greater and the lesser operands. I don't care about left and right because I don't want to reason about whether the programmer did it in a certain direction. I want to know which is the bigger end of the operator. So either I am the greater operand, which looks like this. And so I will bring this comment down here. And I guess polarity or parity is it's in the false part of this that I want. I think this is what I want here. So if I'm in the place where the condition does not hold, it is safe because I bound it below. Or the other case is what I had up here. Something similar, as long as I remember to switch the senses around. I am the lesser, not the left operand, the lesser operand, and parity is true.
All right.
A good way of checking whenever you're writing pieces of a query is to use quick evaluation. You should have done this for the source, but I was in a rush. You can run the command CodeQL quick evaluation to evaluate just this predicate and see what it finds. This will probably find a whole bunch of stuff because it's now going to find every single place in the program that there is a greater than or less than comparison. But it's nice to know that at least I found the pattern that I cared about.
Will the pattern return the body or the actual comparison?
Yeah, it will give me three things. It will give me, because I evaluated this member predicate, I will get this, which is the comparison operation. It will give me checked, which is the expression that I got checked. And it will give me the Boolean parity.
Perfect.
This has done some interesting things with the formatting. Here we go. So in this case, checked is the bigger one and the parity is false and so on. And if I click through enough of these, I'll eventually find the one that we care about, but I'm not going to do that here.
That's definitely a number that you should not do by hand.
Right. So just make sure that your predicates work is always a good stepping stone as you're writing these queries. You can do similarly for sources and sinks. You cannot, I'm not sure if you can see my right click menu. You can see it now, it's a bit of a lag. CodeQL quick evaluation is your friend here. You want to evaluate your predicates to make sure that individually they are correct before you put them into a bigger query.
Mm-hmm.
Okay, with that in mind, let's run the query.
Are we not supposed to connect the configuration? Oh, you already did that?
Indeed, you are supposed to connect the configuration, and I have not done so. So let me not run the query.
Sometimes like CodeQL works in magical ways. So
It has some magical extensions where you can add things, but that's generally a good rule of thumb if you didn't use it. Now I do need to use, I believe it's called Sanitizer Guard. And I will need to give it a barrier guard argument. And I just ask it to use the class that I defined up here, which I called comparison guard. Now I will run my query and actually use the thing that I wrote. While that runs, I'm just having a look at the chat. There's a question about restricting quick evaluation to some subset of the code base because you want to check that you filtered some of these. That's a great question. You can't in terms of changing the tooling. I'll move that out of the way for a second. However, you can always modify your predicate's body to add some filter about the location. So what you might want to say is, I care about sources within a particular file. So I can get its location, I can get the file, I can get a whole bunch of things about the file. Maybe I want just the file name, just the base name, and I can do something like that. So this is a good trick for just narrowing down your predicates while you test them, often narrowing down your results as you test them as well, because you want to see that you've caught the problem in this particular location, starting at this particular point. But I make this mistake all the time. Don't forget to take it out when you are done using it. Otherwise, you will be very sad about why you do not find results that you meant to find. So that is a useful trick, though. Just use the locations to match.
All right, so before we actually go into the results, in the past, without this barrier, we got 21 results. And now it seems we got in 11 results.
That's right. Let me just make sure that's not the one I wanted. That was a different code base. Here we are. We had 21 on Guacamole server, and now we have only 11. Let's have a look at them, make sure that they are. Wait, am I even on the same code base? I'm not on the same code base. Let's run it on Guacamole server, just for ease of comparison. Oops, that's not what I meant to run. Here we go. Where do you specify in the comparison guard that the guard compares the length? Good question. So the comparison guard here is anything that does a less than or greater than check. Because I don't know how far through the program this has flowed, it might be called length, it might not be called length. This is very loose. Now, the real precise way to do this is to say this is comparing against some known length that I am then using from the string copy call. There are other libraries that you can use to say that these are the same expression, but it's quite hard to reason about this across function boundaries. It's quite hard to say like these two are the exact same values and they might be alias, they might be exactly the same. So we're taking a very kind of imprecise heuristic approach here, just saying filter out a place where you've got a bounds check of some form based on the direction of the bounds check.
But is using any sort of like data flows from the source automatically? Like we are not defining the source as part of like this check, right? Because otherwise it's like every check. So it has to be like somehow related with a data flow from the source to that check.
So we are, so the barrier guard will only stop the flow. So we start with the sources that we defined. We will trace the flow through. We will stop if we found these barrier guards, and then we will see if we can eventually reach such a sink.
So interesting. We used to have 21. Now we have 8 results.
8. It's kind of interesting. So I will get rid of my history so there's a bit more space here. I have one of these calls that is not compared as far as I can tell. At least not in this path. We are in the else block of this comparison. So it's, we have one of these, similar pattern. This one is, we check that the length is positive, but we don't check that the length is bounded above.
Okay.
Same business here. This one always happens regardless of whether that bound is checked. These are all kind of quite similar. This one just has no checks at all. Like there's nothing to worry about here. I think these are quite similar. The different parts of a library that is designed to handle file system operations or file system path constructions.
That's awesome.
Okay, so I am happier about those results because it doesn't get fooled by those like remaining macros that actually do the correct recalculation of the length. And this is even more reasonable, even more manageable. It might be, as some people have pointed out, that this kind of sanitizer is either too loose or too precise. Like it might sanitize out more than you want, but you can refine that if necessary. I think it's a really good starting point to see whether you're getting precise results already.
We have a couple of questions. Someone is asking if you want to check for general conditions, we could do if statement correct.
If we trace through these definitions of these barrier guards, they are already the things that are in a condition. So there's this condition that says it is within an if statement or a switch statement or a loop condition. So it's already done that for you. You can, of course, if you want to write pieces of query yourself, you can always say like, look for if statements and look for the condition inside the if statement and so on. But if you're reasoning about barriers and barrier guards, it's it's there already.
Have another question. So there is Sanitizer Guard only consider things that flow from source to sink? Does that mean that any expression from source to sink or anything that use the source? Sure, if I fully understand the question.
So think of a configuration as defining different building blocks. The source is one. Each of these building blocks can exist on its own, right? You can have sources of some vulnerable input, of some surprising value like we have here. They exist in the code. You describe what they are, you find them. Similarly, you can have sinks that say, here is a place in the code I'm doing something dangerous. You can have sanitizers which say, I am comparing some value. I don't know what the value is, but I'm comparing some value against some other condition. I am doing some kind of check, that sort of thing. Now, the configuration is bringing all of these together, right? And so when we do, the real magic is this has flow path, has flow predicate. If we look through the definitions of this and we saw what reasoning it's doing, it is using all of these definitions that we have here and putting them together. It is saying, find me paths through the code where I can start at a source and end in a sink, and I'm not going through any of the sanitizers that you have defined or that I have defined in the standard library. So putting all those together is what the configuration and the flow path predicate do. That will give you a result that says, there is the flow of data or there is not the flow of data in this situation. So you can describe these independently, but for them to be a final result of a flow query, they must be reachable together. And what it will give you is paths from the source to the sink.
All right. I think we are getting close to coming to an end. Do you have any other questions from the stream chat before we actually wrap it up?
There have been some questions about guard conditions, but I think the others in the chat have done a great job at answering them. It's the thing inside the condition is the guard. Inside the if, for example, is the guard condition. If you're unsure, again, you can always experiment, right? Get a database of some open source code, make one on some open source code, write a little predicate that says, find me all guard conditions and evaluate it. See what you get. And that will give you a good intuition for like what these components of the libraries are actually doing. How do you get old results back? If you open the CodeQL view in your VS Code IDE, it gives you a nice query history. You can see all the queries that you run in the current session. You can click on them. You can see the results. You can see the query. You can rename it, do other nice things like that. So this has been, this UI has been improving very rapidly over the last few months. So it's got a whole bunch of nice features for you to track the results that you're doing. And we are open to ideas. So, talk to us on discussions, talk to us by filing issues. If you're trying this out and you run into friction in your workflow, let us know.
I think that if I'm not wrong, if you go like show query text, it will actually show you the original query.
I believe so.
Run.
Yeah.
Here we go. Yeah.
It gives you a read-only buffer of the query at the time it was written.
Mm-hmm.
This is nice if you've like iterated on a query, but you just want to remember what did it look like at the time that I wrote this.
Yeah.
Indeed, this version does not have my sanitizer.
Where can I find a copy of this query? I think that we can easily save it and put it on our repo, github.com/security-lab. We can definitely do that.
Sure.
Or we can actually put it on the discussions.
We can put it on discussions too. That'll be a great place to continue the conversation. Mm-hmm. If you also want to see similar queries that do these kind of patterns, look in, if you've got a copy of the CodeQL libraries, this is github.com/github/CodeQL for most languages. You can see all the standard queries. And if you open snprintf overflow, for example, this is a more complicated version of the query that we wrote. There's a lot of stuff going on here that talks about overflowing that I've not really gone into. But it essentially finds this pattern of finding calls to things like snprintf where the result might flow into the size argument. So it's nice to see how these get used in the queries that we run in production.
Perfect. All right. So just to wrap up, I think that we discussed the vulnerabilities around return value of string copy memory functions, and we took like two different approach. One is sort of like a red teaming approach, which is around building a fast query that finds certain amount of results that are manageable later through manual analysis. And you want to do that, right? You don't want to start like adding constraints where you're like exploring code, because that's what you're doing. You're exploring code, and you might find vulnerability classes that are exactly what you're looking for, but you might find like things that you are actually not looking for through these like basic queries that you're building. As we, sort of like went through that, making those easy queries are much faster and easier to build. Now, on the blue team side, there is this that you have to think about like all the potentially false positives around one vulnerability. So that requires much more investment in it, but obviously it paid pretty well, because then you can add it on your DevSecOps pipeline, and like every time that developer make a mistake or like follow that bad pattern, then you can detect it right away before they actually get introduced into code.
Sorry.
So for everyone here, just want to let you know that we have a Slack channel if you want to ask more questions later in the future. We also, under our GitHub public repo, github.com/GitHub/security-lab, we have a discussions, which is a forum that you can ask questions around CodeQL or anything related with open source security. And finally, you can also visit our website, securitylab.github.com, which has a huge amount of resources. You can download CodeQL in there and compile your own code base as far as it's open source or for academic use. And you have, we have learning labs, we have CTF, we also have a bug bounty that is currently live, where you can write your own queries and merge it with the open source query that we currently had. And obviously you get paid for that. We also have a bug bounty around like finding real vulnerabilities in open source projects with a CodeQL query. It has been very active lately, the bug bounty, and we are more than happy to get more and more results. So, happy to expand this community, happy to be here in this live QL. Thank you, Aditya, very much for helping us. And I hope that we can continue having you as the expert in CodeQL, and we will see other bug classes in the future.
Happy to be here. Yeah, and to answer the last few follow-up questions on the chat, if you're asking about CodeQL training, follow the resources that Nico mentioned. We have learning labs that you can follow. We'll hopefully have some more of these. And for enterprise customers, we of course can arrange things that are necessary, but in the open source and security research world, we have plenty of resources available for you to jump in on.
Yeah, there's a workshop that Aditya and Luke did on satellite. It's like a 2 hours workshop around CodeQL in JavaScript and Java, if I'm not wrong.
That's right.
And you can follow that with examples and all of that to learn to do your first steps into CodeQL. And obviously, we could continue with this live CodeQL. If you like it, please let us know in the Slack or on Twitter or on the discussion. Let us know what you want to hear. Like, if there's anything on CodeQL you wanted to explore, or a vulnerability class that you are curious about, we are more than happy to work around that. In the future, we hope to have like other security researchers and other people from the community to talk about their vulnerability classes, and hopefully, find a way to model them on CodeQL. Anyways, thank you very much, everyone, for staying with us, and see you next time. Thank you, Jeff.